Thank you, everybody. So good afternoon, everybody. Maybe it's a new community for me. So I want to ask you a quick question. How many of you have written a smart contract or know about how many of you have written smart contract? Amazing, amazing. Okay, so this talk is relevant for you. But even if you, smart contracts are interesting. And we're going to show you hopefully something very interesting related to smart contract in AI that John has been working in the last 3 months. Okay, what's going on? Not yet.
There we go. We got it.
Okay, no, it's...
We got it.
No,
we got it. Look.
Okay, no, but I see it here. Just put it slideshow.
We are doing it on slideshow, Mooly. Hang on.
It's not slideshow yet.
Okay.
Slideshow.
We're good.
Then give me this. Okay, so what we're going to show, we want to show you something actually pretty interesting that I think it's really surprising. So everybody thinks that, we are in the age of AI, and you hear that many people say that AI makes code less secure. But in fact, we're going to show you that it's not necessarily the case. So what is the... Oops, it's going too fast for me. So what is the situation in this area of smart contract? I'm sure you have already had. So basically what happened in the area of smart contract, there are these hero developers. There are developers that are very, very smart. And they are developing these smart contracts, and usually it's a very, very lucrative job if you know how to write smart contract. And there's huge money spent using security firms, including our own, that actually make the code secure. The interesting thing is that even if you do all these security, including auditing, fuzzing, formal verification, and many techniques, people are finding bugs. And when you look into the internet, people say LLM will just make things worse because it's going to generate more code, it's going to generate more buggy code, it will make the task of the hackers really, really easy. So is that the case? So in fact, in this talk, we're going to show you that it's not the case. We're going to show you that, in fact, it could be the opposite. It could be that LLM, despite what everybody thinks, and vibe coding, which is probably the worst thing that somebody say, is not so bad. Because vibe coding could be combined with what method called formal verification. And for those of you who are not familiar, formal verification is the art of making the code secure and making formal verification. And the idea is formal verification and LLM, they go along together. In some sense, they are complementary. The LLM is good in sort of anticipating some things, and formal verification really know what the truth is. So in this talk, we're going to show you how you combine it together. John has built a system to do that. So what is the main idea? The main idea is actually pretty old. It goes the way how we usually develop cycles in software. We have a circle of developing software. We start from the design. We go to the implementation. There is testing. There is refinement. There's all of it. But the issue is that there are bugs which are found there. And these bugs are actually making it, and these bugs are identified usually too late. So what we're going to do, we're going to add some spec into the domain. We're going to expect the ability of the user or somebody to write what is the expected properties. And this will allow us to find the bugs earlier, and also to make a guarantee that the code does what it's supposed to do. It's not moving. John, why is it not moving? Okay, so why is it interesting now? So what's going on now, there are two things, of course, if you look into this idea of spec-driven development, it goes back to the early ways of computer science. People were saying, starting by writing the spec. But there are two things that change. Formal verification tools are becoming readily available. For example, we put Certora, which is a tool that almost every developer can use, and Amazon put a wonderful tool which is called Lean 4. So there are these tools that can allow you to use formal verification by engineers. And on the other hand, the LLM is getting all the time better. So that's why we can do this, we can combine them now. Okay, so how is it going to go? So what we're going to do, we're going to allow you to do this provably correct vibe coding. So the user starts with the specification. The specification includes some formal, it includes some interface, it includes some document. We give all of it to the LLM. We give all of it to the LLM, and the LLM is smart. It doesn't get the whole code, but it gets the beginning. So it gets this, of course, you give it a prompt, and you say, and the prompt is something that we engineer internally. In Certora now, we have worked and we engineer internally the prompt, and it says, generate this implementation that satisfies things. And it, for example, you give some kind of spec based on what you expect. You get a code in Solidity. This code is not perfect, but it's the start. And then what will happen, we run this code along the spec, and this is the prover. This is technology that you can have, and you can check the bytecode. If you are lucky and you get the proof, that's great. You get the proof, the LLM got it right from the first, but this is usually not the case. Usually the LLM never gets it right all the way. So this is why we run. So it comes from bugs, and the idea is tools like Certora Prover, they give you an explanation. They say, this is violated under this condition. And then we feed it back. There is a feedback loop. We feed it back to the LLM, and we say, look, give us now a code which does not have this behavior that was there. And the LLM keeps going. And then again, we run it, and after several iterations, the LLM gets it right. Keep going. So this tool is used to be called VeriSafe, but for the purpose of this call, we call it Composer. It's a technology that we are actually working on. It will be released, and you can use it to generate. At the moment, it's for Solidity and EVM, but we can make it work for other things. OK, so the rest of this talk, I'm going to transfer to my colleague, John Toman, who actually built all this technology, and he's going to show you how to build it, and we actually prepared an example for you. It's not a real example, but it's a contrived example that allows you to appreciate this thing. So take it, John.
Thank you. Can you all hear me? Is my mic on? Yeah? Can you all hear me? Perfect.
Can you put John on the...
Can I get my mic? Maybe? No? No, I can't take that. Oh, wait, I think, OK, perfect. We got me. Perfect. OK, so as Mooly said, this isn't working. Yeah, there we go. So our contrived AMM is what we're calling the collective compensation constant product pool. For those of you familiar with DeFi, this is just a simple constant product pool with a twist. That is, larger withdrawals will incur progressively higher and higher fees. So we're effectively redistributing large gains to the remaining liquidity providers, socializing big gains. Now, note that this is a novel idea, not necessarily a good one. And in fact, we specifically chose something that no one has done before, because we want to show that the LLM is able to generate novel implementations. This is pretty laggy, so perfect. So as Mooly said, part of the input is a natural language specification. And so this is a design document that we cooked up for the CCCP pool, written in natural language, just specifying the behavior that is expected for these kinds of this pool. But we also include this formal specification that formally says what the pool must do. This is written in a language it's called CVL, which is a Certora verification language, and this is sort of one of the core rules. It basically says that bigger withdrawals, so LP token 2 being larger than LP token 1, should give you a larger penalty. And that's so penalty 2 has to be bigger than or equal to penalty 1. This is just one of many rules, but it is representative of the kinds of rules you would write for a DeFi protocol like this. So how do we turn this into a synthesized implementation? Well, if you remember the system diagram that we showed earlier for Composer, this is our instantiation of these 3 inputs. And I am now going to play with fire. And here we go. This is an interface that we built for debugging this tool and for seeing how it worked. And we actually see there is a 4th input here, which are a bunch of natural language requirements. Now, the user did not actually write these. These were all extracted from the system document. And so before we ever actually start running the LLM to generate code, we first just feed it in the rules and the documentation and say, analyze the specification and identify any requirements from the system document that aren't necessarily covered by the spec, right? Because it's hard to write formal rules that cover every possible behavior, but you still want to make sure that the implementation hews as closely to the system document as possible. And out of this comes things like the implementation must ensure that the first liquidity provider, et cetera, et cetera, et cetera. And this list of requirements is fed in as well to the LLM. Okay, so one thing we all know about AI is that it can hallucinate, right? And even outside of hallucinations, it can very easily make wrong assumptions or get stuck into some local maxima. And so we need to have some correction mechanism. We don't want this running in 200 loops thinking that misunderstanding how liquidity is supposed to be managed within a pool. And so what we've done is we've added a human-in-the-loop feature where the LLM is allowed to ask the user questions. So should the implementation do this or that? And then the user can provide free-form natural language guidance back to it. And so we can see an example of this here. Nope. Which one was it? So yes, this is an example of the question. No, it's not. Well, whatever. Fine. Never mind. We don't have time for this. So this is, again, very commonly called human in the loop. Okay. So remember, one of the inputs is this specification. And writing specs is very similar to writing code. It is not a foolproof process. Like all code artifacts, specs can have bugs. And so, do we need to have perfect specs from the start? Does this require you, does this basically change the problem from writing perfect code to writing perfect specs? Because then we've really only made kind of a lateral move there. And the answer here is no, actually. When the LLM gets a counterexample and an explanation of the bug that comes out of the prover, the Certora prover, it has the ability to think and say, well, hang on, the spec is saying that I shouldn't do X, but the spec document seems to say that I should. I think the spec might be wrong. And so then the LLM is allowed to ask the user, I want to change the spec. And then it provides a diff that describes the change in the specification. And crucially, the user has to approve this. The spec is the guiding light for your implementation, and the LLM is not allowed to arbitrarily change it. You have to approve it. And you can, of course, also reject it and say, no, the spec is right, you are wrong, fix your implementation. And it will try to adjust to that specification. Or you can give it some guidance to say, please refine instead and do this, make this small tweak instead. Or you can accept the spec change, at which point, this is basically LLM-powered spec refinement. And this is, by itself, quite useful, we found, for taking an initial spec and just putting it through its paces. Does this actually describe the implementation that we're working with right here? And so, after this refinement, we take the new rules, the new specification that was generated by this proposal, feed into the prover, and then the process continues. So, I just asked, do we need to have perfect specs from the start? And I argued that no, the LLM will help you to go through any spec mistakes that you might have. But are we actually requiring that you have complete specifications from the start? Do you need to have your spec 100% upfront, right? So let's work through an example here. RAMM, actually, as I described to you, has a problem. We implemented it, we got some generation, we got some code that came out of it that implements the specification and the requirements document. And big withdrawals definitely incur progressively higher fees, but nothing stops someone from just doing several small withdrawals in a loop, right? Oopsie, we forgot something. There was a bug in our design, right? And so the solution here is to refine the specification. We can add this new rule to our the specification file that effectively says, in the same environment, which defines the current block, if you try to withdraw twice in this same environment, then the second attempt to withdraw reverts. Okay, great. We are able to update the spec, but we've already gotten our implementation. Maybe people have started to review it. Maybe people have started to build components that interact with it. So do we have to start over? Do we have to take the old spec, add this new version, and then just start the whole process over again? Do we have to answer all of the same questions and learn this new implementation, rebuild everything that used to interact with it? And luckily here, the answer is also no. This is something that we call meta-iteration. So we can take these refined rules and basically feed in the previous implementation, which actually usually consists of a lot of files. This is the implementation that came out of a prior successful run. We also include some memories that were generated by the LLM in the previous generation step. It understands, it remembers the answers to the questions that you, or the answers that you gave it when it asked a question. It understands the spec better because it has asked questions to refine its understanding. And then we feed this into the LLM as well, and we also, of course, adjust the prompt slightly to say, please update this implementation with explicit instructions to try to make these changes as minimal as possible. We don't want the LLM saying, I see, I should rewrite everything. Because again, We want to try to keep these changes minimal to make it possible to keep working with this as part of a larger software development pipeline. And then, yes, once we've sent in this prompt and this old implementation, the process continues like usual. So in summary, Composer is a mostly automated code synthesis tool. Again, the mostly here because there is interaction with users for help or for potential edits and whatnot. The code is verified against the final spec because that is what you've refined with the help from the LLM. And we also have this feature for meta iteration when you realize that your AMM has some crucial design bug, or maybe you just want to add new features or whatnot. Okay, and this I will hand it back to Mooly.
Thank you
this
very
is
much.
Not working.
It's not working?
No, just I'll advance the slides.
Okay, so you continue.
Yeah.
So thank you very much, John. So let me just summarize, and then we will be love to get some questions. So I think the takeaway from this, we doing baby step here, and I think we presented it to several developers, and don't be scared. If you are a developer, and you're a good developer, you're going to get a lot of work. This is not going to eliminate developers. But I think it actually makes an interesting case that somehow the AI, when it's instructed properly, it can actually generate code which is almost right. And with the LLM, it can get all the way right. It's also an interesting thing for formal verification. We have been in the last 7 years, Certora is actually celebrating 7 years tomorrow, and we have been in the last 7 years trying to verify some of the most complex code in the smart contract, which is still simple software. But the idea is that often we find out that formal verification comes too late in the development process, because we are getting a code which is very complex, it's all spaghetti, it's not modular, and it's not amenable to formal verification. And what we think is with this kind of approach, we can always maybe have the best of both worlds. So the ingenuity of the programmer is still in the play. But I think what happened is that we know that in all code there are corner cases. And corner cases is hard. And this is actually where formal verification is very good. Maybe it's a rounding error, maybe it's some kind of corner cases. So basically the idea that you have these invariants or these specifications, they serve as kind of a guardrail for the development. And the LLM is learning things more and more locally. The interesting thing is that LLM here is playing several roles. It helps you in writing the code, it helps you in writing the specification, and it's not actually contradicting. So at this point, we are willing to take questions. Thank you very much for listening. Thank you very much. And the credits, beside us, I want to give credit to Leo Oppenheim, who is here as a security researcher, and Giuseppe Gugmazzi. He is in our team, and he helped John in building this tool. They helped John in building this tool. Thank you very much.
Amazing. Thank you for this amazing talk. We can start the Q&A session. So if you have a question, please raise your hand, and our volunteer is going to give you the microphone. We have in the middle row.
Hola, how are you? So you presented this sort of a loop between LLM and coder, and if failing, then get back to the LLM, generate, etc. Is there any formal guarantee that this converges?
No, you could, in principle, continue to adversarially give the LLM different guidance. You could say it to do one thing and then decide afterwards to do a different thing and keep doing this again and again. The key here is that the LLM is explicitly prompted to ask the user for help if it thinks it's stuck. Now again, that's still relying on the LLM to follow this prompt, and we all know how that goes. But there is also the possibility to interrupt the flow and try to correct it. If you see it's basically getting stuck in some local maximum and it's not asking for help. It's just something we didn't have time to discuss in the slides.
But we can actually show you at least one case. We had in Certora, for example, we had a lot of specification for ERC, and the tool told us that these specifications are wrong in the sense that there's no way to satisfy them. So in fact, it found a bug in our own manual specs, because the idea is that, right, the LLM,
yep.
So you're obviously right, because in fact, there's a loop that the LLM, the formal verification, and the human, okay? So, we can all get oscillate, but it's interesting that we are all helping each other if we are operating correctly, right?
Yeah.
Thank you. And are you aware of any sort of theoretical framework to understand this better?
Yes. There are a lot of, the question is, are we aware of theoretical framework to understand it better? So the answer is yes. There's a lot of work in automata theory and others about synthesis. There have been a lot of theoretical think about synthesis, going back to logic, quantify elimination. But the issue with LLM, honestly, I don't understand LLM, maybe John, but they're working very well. So there are things that we don't understand, but they practically work very well. And also we are using SMT solver, which also a bit unpredictable. So yes, there's a lot of theory. There are theoretical results explaining when can you synthesize or not. But yeah, you want to?
Yeah. This is actually a instantiation of a general technique from synthesis called counterexample-guided refinement, where essentially you have something that generates code, and then you check to see whether or not it does what it's supposed to do. And if it doesn't, that goes in a loop. In this case, the thing that proposes the code happens to be an LLM. But this is an instantiation of a very particular technique that's been discussed in the code synthesis literature for, I don't know, decades at this point.
Right. Yeah. So there are work in counterexample synthesis and automata theory, a lot of people on synthesis, but we think it's unique because of the practical usage with the prover and the practical usage of LLM. But if you look into the programming language literature, there's a lot of things. Even Amazon now announced that they are working on a tool similar like this, I think, actually.
Okay, we're out of time. Let's give a big applause